variable Z.
Yeah.
We considered a random variable Z to be a random variable taking a value 1 or -1 with a probability of a half and probability
0.5, yeah.
of a half. And
Yes.
we saw that expected value of ZT becomes 0, and
Yeah.
variance of ZT becomes 1/4, and we call this one just sigma squared of Z.
Yeah.
XT, which is now the random walk, random walk, is defined as Z1 plus Z2 plus up to ZT. And we also saw that expected value of XT is equals to 0, in the sense that this is the same as expected value of summation of I runs from 1 up to T of Zi, given that which is equals to I run from 1 up to T expected value of Zi, which is the same as summation of I runs from 1 up to T of 0, which is going to be 0. Okay. We also saw that expected variance of XT, which is the same as expected value of X squared minus expected value of XT, and everything squared is the same as expected value of XT squared, because this is 0. This is going to be 0, so it's going to disappear. And we saw that this is the same as a summation of Zi squared times the probability of Zi, which we found to be something like this, which we found to be something like this, which we found to be, I think there's a problem. There's a problem. There's a problem. Here. There's a problem here. The problem here. This is the same as expected value of Z1 plus Z2 plus ZT, isn't it? Squared. Okay. Squared. And we saw that this is the same as summation of Z1 squared plus Z2 squared plus up to ZT squared plus plus expected value of bracket 2Z1 Z2 going up to plus 2ZT minus 1 ZT, and all these were going to be zeros. Zeros because they are independent. Then we end up with some expected value of summation, actually. Summation of expected value of Zi squared. I runs from 1 up to n. But this one we saw, up to t, so that this one is sigma z squared. So the answer for this is going to be t sigma z squared. We saw that in our last class. Yes. In our last class, and that means that means
oh, what did I press?
my screen is misbehaving a bit, but now I'm there.
Oh, I don't like this.
Okay. So when we get to our variable of interest, which is the random walk xt, which is the random walk now here, which is given as summation of zi, I runs from 1 up to t. We have expected value of xt is equals to 0, and variance of xt is equals to t sigma squared z. Now, we looked at how we can borrow the properties of random walk to Brownian motion, random walk to Brownian motion. And just to remind you, we had, if that is our scale, if that is our scale for time, time 1, time 2, time 3, time 4, time 5. For a random walk, this one is going to be -1, -2, -3. Is going to be 0. Is going to be 1. Is going to be 2. Is going to be 3.
Yeah.
So for a random walk, xt, I mean, we can talk of 1, 2, 3, 4, 5. So random walk x5 is the same as z1 plus z2 plus z3 plus z4 plus z5.
Yeah.
This one is at time 1, at time 2, at time 3, up to at time 5.
Yeah.
So assuming at time 1, assuming at time 1 we have the realization of -1, then we have -1, then we have +1, -1, -1 again. Assuming we have such kind of realization, that means x5 is going to be -3 in total, isn't it? It's going to be at position -3. So let's see that. So we go down after one time point, it is here. So it comes down like that. And then at time 2, it's -2 now, because it's still negative. It comes down there. At time 3, it's positive, so it goes up one step, and then it goes down again, one step, then it goes down again, one step. That could be my random variable. Okay, that is my random walk. It's given like that. So if you consider reducing the time interval to half, means at every half we do the tossing of the coin or of the experiment. So it means we now consider the timings at the half time. So at half time it can be at 1. So I'm now considering x10. It is x5 but divided into 2. I mean, but multiplied by 2. So it's giving me 10 different time points. So it's giving me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So instead of 5 time points, we have 10 time points. Now, so it means at half of the time we do the toss. At that time, it can be 1 or -1. So if it is 1, for example, I'll have it there. -1. I will have the other one there. Then I can still go back there. Can still go back, come back down. So it is coming. It is just coming after every half of the times that we had previously. So that one can go like that. Can go like that. Can go up again. And then like that. So at the end of it, we are reaching at time 5, as t is equal to 5. Already we have 10 outcomes, different from what we had in red. Okay, if we reduce the time interval further to a quarter, we could now talk of within t equals 1 we have 4 outcomes. So we could have it there, then there, then so within here we have at least 4.
Yes.
At least 4. So that we have it there like that, we have it there like that, we have it there like that, we have it there. And then at this quarter, we could have it again down. We could have it again down here. I'm just picking them at randomly. Could just again have it up there like that. No, sorry. This one should be. Sorry. This one is there. This one is there. This one. Yeah, this is okay. This is okay. And then we could have another one up there again. Up there again. Could have another one up again, depending on what sort of outcome you are going to have from the experiment. And it continues. It continues. It continues to fall like that. So you can see the blue one. The blue one has got so many jagginess compared to the green. The green one has got more jagginess compared to red, isn't it? So the more you reduce, you reduce the time interval, is the more you are likely to get more jagginess, kind of what? Kind of a curve, okay? Like that. Now, the black one is, and of course, the more you reduce this, the more, again, you get your jagginess, experience compared to when the time span is much. And then, therefore, this black one is almost close to brownian motion. Close to brownian motion. So let's now use that kind of analogy to let's use that kind of analogy.
Yes.
What happened? So I'm trying to see what happened. I think my screen just stop sharing. You're not seeing anything on the screen, eh?
Yeah, I'm just seeing you.
Yeah, so I'll be back in a moment. I'll be back in a moment.
Okay.
I'll be back in a moment. Share the screen.
Okay, I'm seeing it.
Okay, now you're there. So that is what we are talking about the brownian motion. Now that means, Joanne, the brownian from random walk to brownian motion, we have here discrete time. Discrete time, and here we have continuous time.
Yes.
So this one happens when you reducing the time interval.
Yes.
I.e., when the change in time goes towards 0. Okay. So if that is the situation, let us get back to our z, the properties of z.
Yes.
We had that z is the random variable that corresponds to the experiment of tossing our coin. But when this interval is reduced and the time interval is reduced as much as possible, we can consider z to be some function t over n. And why we are doing
Yeah.
that, T is the time interval and N is the number of divisions that we are having, so that we have them within one time intervals, 0, 0, 0, T. We subdivide it into so many of the N times, so that our
Yeah.
Z now is not, we are not calling it 1, but we are calling it T over N. Okay?
Yeah.
But we saw that expression value of zk is the same as 0, and
Yes.
the expected value of z k squared would be t over n everything squared.
Yes.
Everything squared. So what happens here is that if we let now, instead of having t over n, just for simplicity, we do the square root of z. Z now is not just t over n, but it is the square root of z over t over n. Then our expected value of zk squared would be just t over n, not squared.
Yeah.
Okay. Now, if that is the case, therefore, then expected value of xt becomes what? Expected value of xt becomes expected summation of for all these zi expected value. And remember, this is 0, so we will have this one also equals to 0. Okay.
Yes.
So the other one, when expected value of zt, of xt squared, would becomes summation. Expected value of summation of zi squared for all these. This is the same as summation of all these of expected value of zi squared, which is the same as summation of t over n. Remember, our z now. Our z now is our z squared now. Summation expression is t over n. So our xt squared becomes t over n summation. Okay.
Yes.
Okay. When we do all these summations, remember we are summing over how many? Remember, we are summing over n of them. We are summing. Sorry.
Sure. What is that note thing that you are using, doctor?
Which one?
This board that you are using, what software is it?
The board, the software.
Yeah, what are you writing on?
No, this one comes with Windows.
Is it the notepad?
It comes with Windows. When you buy a computer, you will always find it there with Windows 10.
Okay.
Yeah. So what is going to happen here? So remember, we are summing over all these, and how many of these do we have? We have n of them. We have n of them. So we're going to sum expected value of xt squared comes t over n plus t over n plus, it goes up to plus t over n. How many of them? There are n of them.
N, yeah.
So it's just the same as n times t over n. N goes with n, and this one becomes your t.
Yes.
Is that correct?
Yes, doctor.
So that means for this discrete case, expected value of xn is equal to 0. Of course, when we are having our time 0, 1, 2, up to n, for example,
Yes.
then expected value of xn squared was given as t. Remember, in the previous area. This is t. Sorry.
Okay.
The Brownian motion, Brownian motion comes in when n is approaching infinity. Remember, we now subdivide this one so
Yes.
that now n are so many. We are realizing we are realizing outcomes from each and every stage of n, from each and every, so we make this subdivision so many of them. And therefore, we have seen from this proof here that expected value of xn becomes just 0, and expected value of xn squared also becomes t. That tells you what? That tells you that variance of xn becomes t, and mean
Yes.
of xn becomes 0. Remember, when n is big, when n is large, we are referring, then xn is a Brownian motion. A Brownian motion. Okay. So in our case, we are referring to now bt. So our xn now becomes bt. So our bt becomes Brownian motion, which is normally distributed and with mean of 0, variance. Remember, the mean is we get it from here, and the variance here we get it from this point here.
Sure.
Okay. So there is one thing that you can that you can realize from this one. You realize that bt is remains finite.
Yes.
Finite. Finite. Why? Because it doesn't change over. It doesn't change to infinity over all values of t. So it means it doesn't matter. It doesn't matter how much time you are having. It means even if I increase this time, I increase this time to almost infinity. Okay. That our t is equals to infinity. Then our bt still will become normally distributed with 0 t. So it just depends on t, but you will get a value that is not infinity. It doesn't explode to infinity. It doesn't explode to infinity. That means we do not care how many subdivisions we are having. We do not care how many subdivisions we are having. Even if the subdivisions are a million of them, what we are taking care of is the value of t here. The value of t here. That's what we are really taking care of. So if these subdivisions, for example, what I'm saying, when we have 0 and then we have up to t, then the number of subdivisions here is 2. Because we have this subdivision and that subdivision, okay? bt still is normally distributed with 0 t. Now, if we move again to now my 0 and t, now we subdivide this thing into how many? 1, 2, 3, 4, 5, 6. So n is equal to 6. Our bt still becomes
normally distributed,
0 t.
Means
now, even if we increase this thing to a million times 0 to t, so that we subdivide this thing, n is equal to 1 million. So bt still remains
normally distributed.
So it doesn't. So the Brownian motion doesn't explode to infinity, even if you increase the number of subdivisions. It doesn't explode. It doesn't. You will still get your Brownian motion, which is ranging between 0 and t.
Yeah.
So
Okay.
the behavior within this range is dependent on the time interval 0 and t, not n. It dependent on the time 0 and t. That's number one. Number two, we are talking of Brownian motion. BT is a Markov process. Markov process. Markov means we are talking of memoryless. Memoryless process. Memoryless means if we are having this time scale 0 t, okay, is okay. So what happens when we want to get the Brownian motion, or the Brownian process behavior from time t onwards,
Yes.
this region here, it only depends on what happened at time t. It does not depend on what happened in the previous time. Okay?
Oh.
It does not happen on what it does not depend on what happened in the previous time here. It only depends on what happened at time t. Time t only is what determines what determines the path, the Brownian paths. We call them the Brownian paths. So that is a property that Brownian motion is also having.
Okay.
Now the other one, which is the last one, is Brownian motion is martingale. You've heard of this word?
Yes.
Martingale. Martingale means when you want to forecast the future price of dollar, for example, today is say today is what's the price today? I saw it is 16.46. It has gone down.
Yes.
I'm surprised. Yes. So if today is this one, if we want to estimate the price of dollar tomorrow, we'll assume that it is only 16.46. A day after tomorrow, we still assume is 16.46. So it means the prices of the prices of this product that we are referring to, we assume it remains the same depending on what price we had today.
Okay.
Now that property is true for Brownian motion, and that property whereby we forecast with only the current price is called martingale property. So Brownian process is also having martingale property. That means what happens in the future, we assume it is remaining the same. So that means when we are supposed to look at returns forecasting. If we have the returns plot up to that point, up to time t, but we want to plot for future. We want to plot for future returns from time t. Yeah, in this region here. What happens? The paths for the Brownian motion start from where this plot ended. If it ended at 16.46, then we don't assume, we don't say that this stock will increase, or the price of dollar will increase or come down. No. Are you together? So that is one property when we'll be modeling using Brownian motion. We need to assume from here, even if the trend was coming down, okay, we say that from this time, when you want to do the forecasting, the trend is remaining the same. Now the paths of your Brownian motions are the one which will run across, but the drift is remaining zero. That is what property of Brownian motion is all about. So even if the trend in the previous days was coming down, of course, somebody will say that I anticipate that even tomorrow it will still continue to come down, isn't it?
Yeah.
But because of the martingale property, we assume now from the point when we reach, we will say that this process now remains to be constant, like that.
Sure.
It
Okay.
will remain unchanged. Now, that is the property. That's one of the property of Brownian motion. When you're modeling with the Brownian motion, you need to have that in mind.
Okay.
Okay. So.
Sure. Okay.
Yeah. So that is what is happening now. There is one property that happens whenever you are working with Brownian motion. Always, whenever you are working with functions which are differentiable everywhere, I hope you are getting what I'm saying. Assuming you have a function that is differentiable everywhere, let's say that's just an xt. Yeah, I'm still exploring some of the properties of Brownian motion. Joanna, I'm still exploring some of the properties of Brownian motion, which is going to be very, very important for you when you are doing modeling using Brownian motion. Now, assuming you have this kind of a function, function ft. This is f of x, okay, or f of t. This is just f of t. It's a function of t. So, if you are having that function, assuming you want to find what is the value of the function at this point, okay?
Mm-hmm. Yes.
What always happens? You can find the gradient of the curve at that point by just drawing a tangent, and then at that point, then find the gradient of that tangent at that particular point.
Yes.
We assume that when you look at this function, this well-posed function here, you will say that at this particular point, this function is not a curve. It is behaving like a straight line, such that you can find the value of at this point by just differentiating or by just finding the gradient of the tangent at that particular point. That is what we always do. And that is where differentiation help. Now, what happens in differentiation when you magnify this curve here? When you magnify it, it looks like this. This one is now more curvical. At this point, it's more curvical. But when you enlarge it, that's what differentiation do. When you enlarge it, it looks like this. You see that? John?
Doctor, I'm here with you.
You need to respond. If you're not responding, I will request you to put your video back.
Doctor, I can't look like that again.
Yeah. So when you magnify this particular point, it will look like this. It is now more of a straight line. Yes. Remember the point that we're referring to is here. If you magnify again, this point, this region here, if you magnify again, it will now look like this, a straight line. Yeah. Now, for the straight line, you can easily find the gradient.
Yes.
Isn't it? That is what differentiation do. But for Brownian motion, it behaves differently. For Brownian motion, it behaves differently. If we have this kind of a curve, and we want to find the value there, that point, the value at that point. If this is a Brownian motion, this is t. Okay. If we magnify this point, instead of getting a smooth curve, we'll find something like this.
Yeah.
So crazy. Now, again, assuming the point that you are referring to is this particular point here. Okay? If you magnify it
Yes.
again, this point here, if you magnify it up again, you will get another thing like that. So there is no point when you get a straight line that you can now make use of in finding difference. I mean, in solving it using differentiation, and therefore that is a problem. This poses a problem.
Okay.
Problem of Brownian motion.
Okay.
Brownian process. That is, you can't use ordinary differential equations to solve.
Okay.
To solve for a point. Solve for a point. And therefore, you need to use what's known as what? What's known as stochastic differential equation to solve. You've heard of stochastic
is there
differential?
something like this?
Yeah.
My goodness.
Are you seeing that? So you'll use stochastic differential equations to solve them.
Yo, doctor, you put me in trouble with this mathematics.
No. This is statistics and you must do the mathematics, my dear.
You know, when we're doing our honors, we kept on asking, is this for math or statistics? Because we are just doing math all the way.
Now, this is now the statistics. In fact, when you now see this one, stochastic differential equation, that's now you are now in the heart of statistics now.
Okay.
Okay. Now, the other property that Brownian motion will possess, assuming you have your timeline like that, that is 0, that is S, that is T, that is Brownian motion at time 0, B naught, that's Brownian motion at time S, that's Brownian motion at time T. Okay? Now,
Yes.
the Brownian motion at time at BT, remember, it is containing all the information that we had at BS and all the information that we had at B naught. Means it contains information in this region here and all the information in this region. So BT is the same as this region, and this region is what? This region is BT minus BS. What happens here? Plus what happens here? BS plus B naught. I mean minus. Minus B naught. Okay? But B naught, we said is what? If you can remember, is 0.
Oh my goodness.
We start from 0. So therefore, BT becomes BS plus BT minus BS. Please don't open the bracket to start solving this and this. Don't open the bracket. This is a random variable on its own. This is a random variable on its own. Okay? Remember, B naught is the Brownian motion from 0 up to T. B naught.
Yes.
Brownian motion from 0 up to T. That's why we are talking from 0 up to 2 is the same as from 0 to S and then from S to T. Okay?
Yes.
That's what we mean. Now, we can look at covariance of BT and BS. Remember, BT and BS, we are referring to covariance. If there is a covariance between this is 0, this is S, this is T, if there's a covariance between this range here and that range. Of course, there should be some covariance because one is inside the other. Isn't it?
Yeah. Yes.
Now, so covariance, the Brownian property, this property of Brownian is so funny. Covariance of BS, BT, BS now therefore becomes, we know BT. BT, same as covariance of BS plus BT minus BS, comma, BS. I've just picked the BT up here to replace it here, isn't it?
Yes.
Covariance is always linear function, so we can distribute this BS inside. It's a linear function, so we can say that cov of BS and BS. Are you seeing?
Yeah.
Cov of BS and BS, isn't it?
Yeah.
Plus cov of BT minus BS, comma, BS. Isn't it?
Okay. Yes.
So what do we have here? This BS and BS, it means BS squared. BS squared is the same as variance BS. Okay? Plus, look at this. Look at this. Look at this. We are talking of BT minus BS.
Yeah.
If we have that scale, BT minus BS is BT minus BS is this region here.
Yeah.
Isn't it? BS is this region here. Are you seeing that independent? One is totally independent of the other. There's no overlap, isn't it? And therefore, this covariance is 0. Are you together? Therefore, we are remaining with only variance of BS. Variance of BS, we said we had BT defined as normally distributed with mean of 0 and variance of T. BS also, on the other hand, could be normally distributed with mean of 0 and variance of S. So it means the variance of BS is S. So this is going to be S. Okay?
Okay.
Yeah. That is the property, some of the properties of Brownian motion. And I think with that gives you some understanding of how Brownian motions behave, Brownian motion behave. Now, I want us to have a very short break after this 1 hour. Already it's 1 hour. Very short break. To just grab a cup of coffee, and when we come back, now we are going to see how we can now make use of the Brownian motion in modeling volatility.